All right, and hello and welcome to Algorithms Live. Last week, I went out to TCO in Austin, Texas for this regional event. So it was really nice meeting some of you from the University of Austin, or University of Texas at Austin. And it was a really great event, a lot of fun. Enjoyed that one, sure. This week's episode, what we'll be doing is covering this problem. Well, more than just one problem. I'm basically going to give a really deep look at the knapsack problem and some of its closely related problems, which is subset sum. And really the idea with this episode is we'll just be learning all these tools to build up to this problem called Joule Thief. And that'll basically end the episode. So we'll just gradually learn more and more stuff and get all the way to Joule Thief. So without any more delay, let's dive right in and see what we can do. So we'll start off with a really basic description of Knapsack and how Knapsack works. Is you basically have these items. Maybe shrink my pen a little bit. So we have an item like. So we have an item. And so there are two values here. So we have this RI value, it's a reward for taking that item, and WI value, that's the weight that the item has. And we basically have a sack that we'd like to hold these items in. And so there's our sack. So there's the knapsack part of the problem. And this sack has some max size. So what I'll do is I'll call that max size S. And the idea is we have a bunch of these items. They're just all items that we can select. And I like to pick a subset of items and have some criteria. So I want the sum of the weights to be less than or equal to S. And I want to maximize the sum of the reward, whatever that reward is. And that's basically the description of Knapsack. And this is kind of a classic problem that you see in computer science. So let's look through an example. Just a quick example of just Knapsack and how this works. So we have maybe something with 4 reward. We have 10 kilograms. And that's an item, or we have something with 3 reward. And so I don't use metric in my day-to-day life, and so I have no idea how heavy this is, like relative to other objects. So this could be embarrassingly heavy or embarrassingly light, and I'd have no idea. But here are just some example items. And what we could have is we could have like a 20 kilogram sack. Maybe that's the max it can hold. And we'd like to select some subset of these items. So maybe if I select these, then it fits within the sack that you can see that's exactly 20 kilograms. And my reward is 10 or 11. But I could also maybe change the weight to 19 kilograms. And so if that's the weight of the sack, then I'm in a little bit more trouble. So I have to find something with a different weight here. But I could get away with, I think if I take these two, I can get the cost to 10, and I don't think I can do better. But you basically just pick a subset of your selection, and then you end up trying to get that maximum reward. Okay, so there's 2 variants of this problem that come up quite a bit. And so let's just talk about the difference. So the variant I just described was sometimes known as 0 or 1 knapsack. So your first thing is you can either take the item or you can choose not to take the item. And so the big thing I want to point out here is this problem, given how it's given, is NP hard in general. So if our values like Ri or Wi and S for our sack size, like if these values end up being really big, maybe up to 10 to the 9th or something, or even bigger than that, you could even get, then there's really not an efficient solution in terms of n, which is the number of items. So what we're basically going to be discussing here is this thing. It's a pseudo polynomial time algorithm. So you can't get a polynomial time in general, and it's just dynamic programming. And so what they mean by pseudo polynomial is these values can get really big and then you're out of luck. But I'm basically, the idea with the knapsack solution is taking advantage of the fact that one of these values or some combination of these values isn't very big, because they'll be part of our state in our DP. All right, so let's take a look at how you solve this. So the pseudo polynomial time DP that I'm going to discuss, it's efficient for small values of S. Okay, so here's our state. So in terms of thinking of dynamic programming, I always think of two things: state and transition. So my state, I'm just going to have I as the item I'm considering. And W is going to be the weight I've taken so far. So it's the sum of Wi taken so far. And this gives us a fairly reasonable size for our state size. It's just going to be the number of items by the maximum sack size that we could have. And I should point out another thing I'm assuming in this problem. I'm assuming all values are integral. So in other words, all the values are going to be integers. Okay, so let's look at the transitions. So the transitions, if I'm at position I and W, I have two options. Either I choose to take the item, and if I take the item, I move on to the next item, and I increase the weight that I've taken so far. Otherwise, I move on to the next item, and I don't increase the weight. And then I just add that transition's cost of like how much reward I got for making decisions. This is take and don't take. Okay, so that's your classic knapsack. So then there's also a second variant of knapsack that's also pretty useful, and it's called 0 and infinity knapsack. So 0 infinity knapsack varies. The main thing here is we can take any number of an item. So in other words, if we're taking k items, it can be anywhere from the range of take 0 of that items all the way up to infinity. So it's like an unbounded knapsack. You can think of it that way. All right, so we could also do this with dynamic programming as well. So this is kind of the recursive memoized dynamic programming again. And I'll just... So let's first talk about how this could be accomplished naively. Or actually, let's not talk about that just yet. Let's talk about the state first. So the state's the same. So if you're doing 0k knapsack, or 0, 1 knapsack, 0 infinity knapsack, the state's the same. So it's the item considered and the weight, which is just the sum of the weights taken so far. So this is the same. So we're still down at n times s for our state. But then we get this problem with transitions. So one thing we could do is we could be at position IW, which is I'm at this particular weight, I'm at this particular item, and then I have to loop over, do I take 0 of the item? Do I take 1 of the item? Do I take 2 of the item? Do I take 3 of the item? And so if we're not careful, what we could have is something on the order of S, because maybe something is weight 1, our transitions could be O of S. And what I really want is I want an n times S knapsack. So if we're a bit clever here, we can actually get the transitions down to just 2 for this in 0 infinity knapsack. And so let's do that right now. So here's our transition change. What we're going to do is we're going to stay at the same item, but now we're going to increase the weight we've taken and then get the reward for that item. So I'm basically allowing myself to hit the exact same state again, but I just have this increase in weight. And then over here, what I can do is I can move on to the next item without cost. And so it's the same state, but now I'm being a little bit smarter. I can stay at position I and then continually take items until I'm okay moving on it. So it's embedding the transitions into the state, which is kind of nice. So now our total runtime for this approach is O of n times S. So that's pretty good. So that's 0 infinity knapsack. It's the same idea as 0, 1 knapsack almost, except the transition is ever so slightly different. Okay, so that's the very first approach we can deal with knapsack. I want to talk about the thing that's going to help us a lot on this problem, or the harder version of this problem, and that's the iterative DP that's space saved. So here's the idea I think of for the iterative DP. And I actually think of this in the lens of solution bags. So it's almost like I have a bag with all my partial states, except my bag happens to be a table. And so here's the idea for my table. I'll draw the table here. And each of these values, all the way up to S, what that's going to represent is how much of the sack I've filled up all the way up to S. And so if I'm at position I, like I've taken I items so far, this table, what it's going to represent is how much I can, or how do I get to each level of filled after taking the ith item or up to the ith item. So now what I can do is, instead of thinking of it as this two-dimensional DP, my only job is to go from I haven't taken item I, and this is right before taking item I. This is what my DP table looks like. And so should point out that if I'm at table of whatever my W value is so far, then that's just the sum of the RIs I've taken so far. I need to take that value and then go to item I plus 1 and get a new version of that exact same table that has all the answers after taking item I. And so that's my goal. That's what I want to get up to. So I'm going to show you how to do it iteratively, because and I'm just going to work one by hand, and it ends up being fairly easy code. And there's this kind of neat trick to coding it iteratively that I think I like. So here's my example using this technique. So let's say I have something that's 3 in cost and that's 4 kilograms, or I have something that's 2 in cost and it's 1 kilogram. Three kilograms, maybe something like that. Okay, so let's do this with 0 or 1 knapsack. See how this thing works. So I want my different reward amounts. So I'll draw out a table. So 0, 1, 2. Put in some dividers. something like that. So initially, this table is at 0, and then everything else is negative infinity. This is if you want exactly that cost. If you want up to and including that cost, you can actually replace these with all zeros and it will still work. But to make things a little simpler, I'll make it exactly that size knapsack, and you can just run through after and find the answer. Okay, so what we're going to do is I'm just going to run through this table and increase it for my first item. So I look at my first item. I can't improve any of the negative infinities because they don't actually help. But I can improve this one at 0. So that one's 4 kilograms. So it comes out here, and this cost ends up being 3. And so you'll notice on the second update, where I end up doing the 1 kilogram item, I need to update this whole table for the 1 kilogram item. I'm going to sweep from right to left. And so what I'll do is that 1 kilogram item, I see that I have a 3 to update. So I can update this to be 3 plus 2, which is 5. And I keep sweeping from left to right. I get to the 0 to update. So I get 0 plus 2, and so this comes out to 2. So now I can sweep through the third item, and I can just sweep through from this value. So this one has a jump of 3, so I can start at 5, and this comes out to 11. I sweep over here to 4, and this comes out to 9. And I sweep over here to this, and so this is 1 plus 3. It's going to update this 4 to now be 8. And then out to this one, 3 kilograms is 6. So you'll see what I can do is I can just write 2 for loops if I was to code this one out. And the innermost for loop will actually go backwards. And I can just update by making jumps to the right of size the number of kilograms that I have at that time. So it's an iterative DP. It's space saving, but it only uses like one table, which I think is really neat. Okay, so what do you do if you want to do 0 or infinity knapsack? So I'm going to show you how this works. So we're going to go back on our table and look at the 0 infinity. So the 0 infinity knapsack is exactly the same as 0 1 knapsack. The only difference is we're going to go from left to right now. Okay? So initially everything's 0, and then there's negative infinities. All right, so we come out to here. We have this thing that's 4 kilograms. It can jump up. This comes out to cost 3. So it's jumping in that direction. And then I sweep over again, and then I can take this cost 3 again, and I get something of cost 6. So you'll notice when I'm sweeping from left to right, I can use the thing I've just updated to update the next one. And so this is kind of a neat trick to making the amount of code I have to write for the 0 infinity knapsack not as long. Okay, so let's take a look at the, let's just update it for the whole table. We'll come out to this 1 kilogram one. So this will basically keep updating our table. And so on. It turns out that 3 was mostly useless. This 1 kilogram thing is quite good. Maybe I'll change this to be a 7 to make things more exciting. 10, 12, 14, and 16. Okay, so now we take the 7, which is going to be a size 3 jump. So I consider using my 7. So it comes out to 7. Comes out to 9. So this is going to be a bit boring. 7, 9. Size 3 jump. 11. But then I can use the 7 twice, so I get 14. 16. And 18. Something like that. And so you can see that I can just do knapsack 0n knapsack 0k knapsack, and I get our 0 1 knapsack or 0 infinity knapsack's almost the same code. Okay, so when I was trying to come up with this problem, basically I knew about the 0 1 knapsack, I knew about the 0 infinity knapsack, and the question I asked myself is, well, what about 0k knapsack? Yay. And so that's the question I wanted to ask myself, and I thought that it needed answering. And so what I mean by 0k knapsack is you have a bunch of different items, and for some of the items, you know that you can take it at most k times. So you can take it any number of times on the interval from 0 to k if you were given k. And maybe those values are different. So maybe I'll call that ki. And I'll call this big K value is the sum of all the different ki values that exist. So this is pretty easy to do naively. What I could do is I could have an n times k SDP, right? So I just do the 0 or 1 knapsack, except for every single item, I just duplicate it k times. So now I have n times k items, and I just run the knapsack. And that's naively, that's fairly slow. And so the question I wanted to know is, can I do it in number of items times the sack size? And it turns out this answer is yes. You can actually do that in that runtime. And so that's what we're going to be heading towards, is try to figure out how to do the 0k knapsack. So what we're going to do is, in order to learn this technique, is jump over to a different problem and learn a technique for subset sum, speeding up some special cases of subset sum, and then try to map this back to knapsack because they're two closely related problems. So the first problem I'm going to talk about is this problem called the partition problem, which is closely related to knapsack. And particularly, we need the partition problem. If you look in the blog, I talk about this problem called polarization. So if you just look up the blog post for this episode, you can see I share a link to this polarization problem. And that's a hard graph theory problem. But as a subproblem, you have to solve this partition problem pretty efficiently. So what's partition? So partition is we have some items, and they all have weights. And what we like to do is we like to partition the items into two sets. So let me give you an example. So let's say we have 10, 4, 11, 8, 9, and 6. Maybe those are items. These are just the weights representing those items. So what I'd like to do is I'd like to just partition it into two groups, A and B. And the goal for this is I'd like to minimize the difference between the two groups. So I'd like to partition them into these two groups as evenly as possible. So I'll do maybe 10, 4, 11 over here, and 8, 9, and 6 over here. So I kind of put them in order. You might be able to do better than this. So this gives me 25 on the left and 23 on the right. So it's off by 2. You might be able to get 24 and 24 if you're careful. But I don't see how to do that. Oh, yeah, here. Maybe if I swap these two, what I'll get is 24 and 24. And so I just want to minimize the difference between these two groups. That's the goal of this partition problem. Okay. So that's the problem you have to solve in polarization. And the problem is polarization, you have to solve it efficiently somehow. And that's how we're going to get around this. Partition problem is also NP hard or NP complete, depending on the variant that you have. And so the variant where you have to minimize the difference between the two groups, that one's NP hard. And so what we'd like to do is it's very closely related to this problem called subset sum. So you can solve it by reducing partition to subset sum, and that's exactly what we're going to do here. So subset sum is you have some items, you have n items. Can you pick a subset of the weights such that the sum of those values is equal to some target value? And that's what we'd like to find. Can we do that? And then so partition problem is easily a special case of this, because what you do is you take the sum of all the elements, and whatever you didn't take is going to be the other group. So what you really want to do is you want to get the sum of the weights as close as possible to the sum of everything divided by 2. You want to get that as close as possible to that value. So you can just make the sum of weights you're taking be the smaller group and build a table up to s divided by 2 and solve this partition problem efficiently. Just see where you can, how you can do that efficiently. So we'll talk about how to solve this similar to Knapsack in a second, but I want to come back to this polarization problem and talk about why we can't just do this efficiently with the naive subset sum. So what we have here for polarization, once you reduce the problem, so figure out how to get the graph theory elements out of here and reduce it to the partition problem, which is kind of neat. A requirement here is the sum of the weights you have has to be less than or equal to some s value. And so we'll have n is maybe up to like 10 to the 6th. I can't remember what it is in the problem. And s is up to 10 to the 6th. So we have up to n elements. They're all up to 10 to the 6th. And this total sum is up to 10 to the 6th. But we guarantee that if you add all the weights together, then they're going to be less than or equal to the total sum. So if we want to do this with like a knapsack style DP, then we're kind of in trouble because n times s is way too big. This is just a way too big of a value. And so, yeah, we're up to 10 to the 12th, and we're not going to get that to run in time. So the main thing to realize about this subproblem is the number of unique items is small. Well, smallish, I guess I could say. So let's talk about how we make these values unique. Because if we make them all weight 1, if we make all the values weight 1, then we're not making any more unique items. So what I'll do is I'll just make the first value weight 1, the second value weight 2, the third value weight 3, the fourth value weight 4, and this just keeps going like this, right? So if I look at the sum of the weights, well, the sum of the weights has to be less than or equal to s. That was one of the requirements I had in my problem. I can't, it's a graph, so you can't divide the nodes up to be more than n, is kind of how this constraint breaks down. So what you'll realize is the sum here, the sum value ends up being n times n plus 1 over 2. So that's just a formula for summation. And that's almost n squared. It's a little bit less than n squared, but we'll just approximate here, roughly. And so what I'll get here is n has to be less than or equal to the square root of s. And so this is the max number of unique items, roughly. And you can calculate it exactly if you want. So if we come up with a way of dealing with items that can have, maybe there aren't that many unique items, but efficiently deal with k occurrences, because if I made them all 1, I have to efficiently deal with having 10 to the 6th ones in my subset sum problem. If I find a way to deal with that subproblem efficiently, then what I can do is have a very efficient way of solving this polarization problem because there aren't that many unique items. So that's what I'm going to get down to. So this brings us back to subset sum. Can we solve subset sum efficiently if we know that there's some item we have to take k times? Okay, so let's take a look at the iterative subset sum solution. So it looks something like this. Instead of having weights in terms of our knapsack, we just have at position 0, we have true, and then everywhere else we have falses. And so if you want to do 0 or 1 subset sum, well, then you could just go this way. And let's say I'm upgrading a size 3 group, then I just, if it's true, then I make the next one true and so on. And so that's how I do 0, 1 style. Or I could repeat taking an element and do 0 infinity style by going from left to right. So it works very similar to Knapsack, except there's a way to do 0 or k knapsack efficiently, or 0 or k subset sum. And so here's the idea. Idea is change the order of the table. So we're going to be updating this table. And you're noticing if I reuse an element, so if I reuse something like 3, let's take a look at how 3 jumps. So it's going to jump here, it's going to jump here, it's going to jump here. Now, if I started from 1, if I was going to reuse elements of 1, it goes from here to here, from here to 7, and then 7 goes to 10. And so you'll notice that those are all consecutive. So what I'm going to do is I'm just going to update every single congruence class at the same time. So I'll update everything where it's my index, so I'll call it I, is congruent to 0 mod 3. And then when it's congruent to 1 mod 3, and then when it's congruent to 2 mod 3, I'll just update those groups together. Instead of just writing a normal for loop, I'm just going to make those size and jumps. So let's talk about what this looks like. So if I take something like this, what I'm basically doing is I'm taking this group, this one, and this one. And what I've done is now I have like true, false, false, true, false, or yeah, true, false, false, false. And what you'll notice is the updates are all now contiguous. So instead of having these big jumps that are going on in our table, we can just update contiguous ranges. So let's take a look at what one of these updates looks like. So imagine I've already done this transformation. If I do break this into a bunch of different for loops, one for each congruence class, the total runtime will be the sum of all the elements in the table. So it's still linear. I'm just going about it in a different order. Okay, so now we can use this kind of sliding window technique. So we have true, false, true, true. Maybe what I'm drawing here is what the contiguous region looks like after you do this transformation. Maybe something like that. Okay, so maybe my table size, my window size is 3. So I'm going to have a window size of 3. So I'm looking back 3 in my table. So I'm going to slide from right to left, kind of like my 0, 1 knapsack, except I'm going to look at a contiguous range of elements and see how many trues there are. So what I'll do is I'll keep track of the number of trues in my window. And that's just the counter. All right, so I don't have any trues, because if one of these trues was true, if one of the things k jumps of size, whatever size I'm updating is true, then I can make this element true. So I look at that contiguous range, that's false, everything's good. So I slide my window. If this was true, I would subtract 1 from my count, which my count's currently 0. And then I just add the end of the range. So this is false, slide my window. So I slid my window here, I update this cost to be 1. Slide my window again, update this to be 2. So what I should have done is update this to true. So I slide my window again, this becomes true. So now that's cost 2. Slide my window again, this is true. Slide my window again, this one is also true. And I continue on until this also ends up being true. So you can update this number based on what's in the window. So if it's at the end of the window, you decrement that value. At the beginning of the window, you increment that value. And you just keep a sliding window of what you've seen so far, and you just update the elements of your table. So the important thing here to realize is the sliding window is O(1) to maintain. So this basically says that we can update the DP for our subset sum. So if we're doing 0k subset sum, the update is an O of S, which is our table size, or our maximum sack size, O of S per item. And that's the runtime. So this brings our runtime time down to, for subset sum, n times s subset sum, regardless of what our k value is. So it doesn't matter what k is, it could be the size of the table, that would be fine. It also means that because it's that runtime, for the polarization problem, our runtime is s times square root of s for solving partition problem, which is a really good runtime if your size of your table is near 10⁶. I think that problem is a 250,000 in size for n. But you can do something that's s times square root s in runtime and solve partition problem. So check that problem out if you're looking for a challenge for subset sum. Okay, so that's how you solve 0 to k subset sum. Let's try to map it back to Knapsack. All right. So 0, 7. So maybe this is what my Knapsack table looks like for contiguous range. So it's something like 0, 7, 8, 4, 2, 11, 21. Something like this. Well, once again, what I like to do is a sliding window. So here's what the sliding window looks like. I'm looking 3 behind myself, maybe. And so here's what the update looks like. Is I have WI is fixed because I'm assuming I've already done the technique of reordering the elements so that I can update them for every congruence class. So for every group of values mod WI, that's what I'm updating right now. So I've done that transformation. These are all contiguous now. And what I'd like to do, the only thing I care about is this Ri. And so maybe I'll make Ri equal to 4 for this example. Well, I happen to know that to update this value here, I'm going to take whatever's in my knapsack there, and I'm just going to take my item 1 time to get to 21, take this item 2 times to get to 21, or take this item 3 times to get to 21. And then I need to be able to slide this window. And now this one is taken 1 time, this one's taken 2 times, this one's taken 3 times. So I need to do some kind of sliding window-like technique to solve this problem and get this one correct. So here's what I'm going to do. I'm going to look at this kind of like a function. Let's say x is how far away I am from this ending location. Then I can look at these all like functions. So x is how many times I need to take something, plus 11. So it's 4x plus 11. This next one ends up being 4x plus 2. And this next one ends up being 4x plus 4. And so what you'll see is these all look like lines, and they all have the same slope. Another way you could look at them is maybe they all have the same x value, but they're just offset from each other. So it's like x minus 2 plus 11, 4x minus 1 plus 11, and then 4x minus 0 plus 4. All right, maybe this is 2. So I could rework the cost this way. So let's take a look at what this looks like. We'll get something like 4 times 1 plus 11, which is 15. And we'll get something 4 times 2 plus 2, which is 10. And 4 times 3 plus 4, which is 16. And we want this 16 because that's the one that's going to update our value the most. But it's not going to override our 21. But we basically, out of all these lines in our window, we have a bunch of lines in our window. We need to find the one that's going to get us the maximum sum possible. All right, so then we also have to deal with our window sliding. So we need to efficiently update for a window sliding. So 4 times this plus 2, well, this is going to be 6. 4 times 2 plus 4, well, this is going to be 12. And so the thing I want you to observe here is the difference between these two values still ends up being 6. It doesn't change. And this happens to deal with the fact that these are all the same slope. So our constant on the end doesn't change. And then the distance between the x values, this 2 and 3, and this 1 and 2 doesn't change. So our cost between the values doesn't change. So what we can do is basically just observe that for each of these lines, if one of these lines is better than another line at the given moment, then it's always going to be better. So what we can do is just maintain a max queue. So if you've seen in a previous episode, I discussed max queues, but you can maintain a sliding window and always know what the maximum value is for that sliding window. So I can do is I can just maintain this sliding window. As I add an item, I add it to the back of my max queue. And I just maintain this invariant of always keeping the best things at the bottom, or potentially better things later on are stored up behind it in the max queue. And then I just do the sliding window from left to right. And it's much like that subset sum. Instead of having a counter value, I have this max queue. So the runtime update is O of S update per item. So in other words, what we can do is we can solve 0 to k knapsack in this runtime, n times s, which is pretty good. But when I saw this, I thought it was too boring for a problem. So I thought that, okay, this idea is pretty good. I figured out how to solve 0 or k knapsack, but I felt like the problem maybe wasn't interesting enough for a contest. So here's what I did when I wrote Jewel Thief. I made one more modification to make this problem a bit harder. And this is what I came up with. So now we have up to 10 to the 6th items in our knapsack. Our sack size can be up to 10 to the 5th. And our weights So the weights of the items can be up to 300, and the rewards can be up to 10 to the ninth. So if you do an n times s knapsack, this is still too slow. That's up to 10 to the 11th. That's not going to run in time. But there's you could have every item in this sack be unique. But the important observation here is the number of unique weights is small. And so it's not the number of unique items. Every item can be unique, but there are at most 300 distinct weights. So I could have made the weights larger. They could have been up to 10 to the ninth or 10 to the fifth or whatever. The important piece is the number of unique weights is small. And that's really what we're taking advantage of to get this. All right, so let's talk about how you end up solving this idea. So the first step is to cluster items by weight. So maybe everything that's weight 3, I have a bunch of different rewards. Maybe there's one that I get 2 reward, 4 reward, and 8 reward. Maybe I cluster the ones that are weight 5 together. So 7 reward, 6 reward, 3 reward. Maybe I cluster the ones that are weight 7 together, and I get 2 reward and 1 reward. All right, so I jumped around. So there's a greedy observation here that we can take advantage of. So if we have 2 values that are exactly the same weight, it's always better just to take the one that gives us the most reward first. Take best reward at a given weight. And that's the idea. So in other words, sort. So we're going to take these lists that we have right here. We're just going to sort them from largest to smallest. Okay, so then the next thing is we need to update all items with weight WI quickly. Because there could be quite a few of those items. So the first thing we're going to do is we're going to use that same subset sum trick. We're basically going to group them together by their equivalence classes, and that ends up, I'm going to update everything that's congruent to 0 mod my weight, everything congruent to 1 mod my weight, everything congruent to 2 mod my weight. So that way I'm only updating things in my table that are contiguous. So maybe this is what my table looks like so far. And instead of doing the exact knapsack, what I could do is fill my table initially with zeros so that it's always an increasing function. So I could skip over some amount of my sack that wasn't used initially. So this is what my value looks like. So now I want to update some ending position. And I have a sliding window. So here's what my sliding window looks like. Maybe from there to there. So if I'm here, this is basically I only want to take 1. If it's here, I only want to take 2 items, and so on. And so a lot like the line problem, I want to basically have some sort of a function saying that if I'm here in this window, that I take only 1 thing in that function. If I'm here in this window, I take 2 things in that function. And if I'm here in this window, I take 3. And I want to maintain a bunch of these functions and see what they look like. So let's take a look at what the function looks like. So I have f of x. And so x will be the number of items I'm taking. So this is x is 1, from here is x is 2, and that x can slide as I want. So what I want to do is I want to have a sum of x values from I equals 1 up to x of r of I. So that's the reward of taking the first item or the second most expensive item or the third most expensive item or something like that. Plus c, which is a constant for my thing like this. This is what my function looks like. It's not quite a line, and it looks a little bit weird. So I'm going to draw this thing out. And so I've gotten some graph paper out here. Let's take a look at what this looks like. So let's say I have 5. Let's say my things here are weights 5. Yeah, maybe 7, 3, 2, and 1. Maybe those are my rewards. Right. So I could draw out the start of my shape. So in terms of the xy plane, this is x equals 1, right? And so out here is x equals 2 and x equals 3. In terms of going up here, well, this is the c for my function. This is how high I'm going up in terms of my function for that constant. So then I need to go 7. 1, 2, 3, 4, 5, 6, 7. So it comes out to that position. Come out to 3. Comes out to that position. That's a 2, and then 1. All right. So I get a line like this, line like this, line like this, line like this. So this is what my function looks like. So it's not quite a line. And you'll notice that this is R1. This length here is R2, R3, and then R4. So that's what it looks like. So this looks maybe a little bit like a sloth arm. I guess I could call this shape a sloth arm. It's kind of like a parabola. I guess you could call it a discrete parabola. But it's basically just going up by 1 for each of the values as it's shooting off to the right here. And so it's not quite a line. And so this is what my shape looks like in terms of the parabola that I'm trying to optimize in terms of this knapsack problem. Okay, so let's go back and think about this. The important thing about the shape is if I'm updating it for a given weight, all these shapes are going to be exactly the same. The only thing that's going to change is where that shape exists and how high its c value is in terms of this equation. How high does the c value get? Right there. Okay, so let's take a look at what these functions look like. So this is the closest one, and maybe it looks like this in terms of a parabola. But then the next one could start over here, and then it's moving slowly to the right like that. And then the next one maybe starts right here, and it's moving slowly to the right like that. And what you're going to notice is I basically have a bunch of these shapes. They only ever intersect at one point because they're all the same shape. They're just offset from each other ever so slightly. And what I'd like to do for all these shapes is maintain the maximum along this curve for the interval I care about. So once again, if you remember the convex hull optimization episode, this is basically convex hull optimization. Except instead of lines, we have these sloth arm shapes, or discrete parabolas, if you want to call them that. So we want to maintain this maximum as you go, except we have these really weird shapes that we want to maintain the maximum from. So we need some sort of invariant to do our convex hull optimization. So let's say this is index I in our table. So we want to, for whatever our window is, ijk, we want to maintain that if I is less than j is less than k, that the time that j overtakes k is strictly less than the time that I overtakes K in terms of our stabs. So if I'm starting right here, well, this line is clearly the best one if I'm starting like out here, but eventually the second line might become better as I'm sliding from right to left in terms of my window. If I hit the end of my window, I might have to remove one of these curves from my data structure. So I'm going to maintain a double-ended queue with all these curves. And then as I add a new curve, it could delete some other curves intermediately because it has to maintain this invariant. All right, so you need to solve for the intersection point between these two curves in order to do this efficiently. And if you look at this shape, this sloth arm shape, there's not really an equation that could help us here. So we look at our old friend binary search, and I can basically just binary search for this time overtaken between two curves and ensure that the time that J overtakes K is less than the time that, or maybe greater than the time that I overtakes K. So J has to be relevant in terms of being in the middle here. And that's all you do. It's just a convex hull optimization after that. Let's talk a little bit about runtime. So the first step in this problem is we have to do n log n sort. So we bucket every single item by their weight, and then we sort by their R values. So we need to get those decreasing rewards for every single bucket. And the next piece in the runtime is for every single one of these buckets. So we'll call that W, big W. That's the number of unique weights or number of unique buckets we have. We also have a log n component. That's the binary search over the sloth arm that we're going to have to do every time we check if two curves, one overtakes another one. And then since we're updating every element in the table, that's O of S. So what we do is for every single bucket of size W, it's a S log n update to the table. And so we get the next row of the table for every single weight value in S times log n runtime, which was good enough to pass. It's got very low overhead, which is nice. So we don't have to worry too much about the runtime. And so that's how you solve the problem Joule Thief. So I hope you all enjoyed this problem and learned a bunch of stuff about how to solve subset sum quickly, how to solve this weird variant of Knapsack, or maybe one of the tricks for 0 or 1 versus 0 or infinity Knapsack. But yeah, it's closely related to convex hull optimization, as it turns out. All right, so thanks for tuning in. Next week, not sure what the topic will be, but I think we'll be back at our usual time of Friday at 9 p.m. So be sure to tune in next week.